Okay, so our next topic, page indexing and retrieval. Basically how Google stores the pages, how it retrieves them back. So we'll start off talking about why it's necessary, basically what the world would be like if you didn't have indexing. And then the second thing is how Google makes it faster, because you always want to do it faster, especially considering the scale that Google's operating on. Then eventually we'll talk about how Google's index system is built, so architecture, components, and then how it works. So first thing, Google's fast. It's super fast. Doing a reasonably popular search on Google takes about half a second to get you the first page of results. An unusual search can occasionally take more than a second. It's rare, but I've seen it happen. I've never seen one take more than 2 seconds these days. So let's do a search. Let's do a popular search. What is a popular search today? I don't know. How about Bitcoin price? That's probably a popular one. Boom, less than half a second, right? It's lately been on a tear. I'm not telling anyone to buy Bitcoin. Okay, what's an unpopular search? Well, part of the problem is unpopular searches tend to not have many pages, which makes the ranking process a little sore. So it sort of equalizes out. But let's do things from different corners of the world. Give me a Japanese word. We'll just go sayonara, unless somebody's got a better one. Konnichiwa, yeah, that's about equivalent, but we can do that. Konnichiwa, I can't spell it without konnichiwa. Okay. Let's see, that'll do. And then budgie, of course. And then what's a city in Colorado? Smaller city. Let's do Telluride. That's a good one. Okay, yeah. And let's see. One thing else. Something from South America. Something. Television? Tarantula. Oh, excellent. Okay, that's probably a pretty unusual search. 668. It's tough to beat. Okay? Yeah. Anyway, so Google's super fast, because you know this is a weird-ass search that doesn't come up very often. But, yeah, part of the problem is, oh, look, this one actually has the words. Just like a random, pile of words. Yeah, top, least probable words, whatever. Anyway, yeah, ranked word lists. There's a lot of this data out there for people who do, language studies, search engine tests, stuff like that. Anyway, all right, so there are some, whatever. It's hard to find. Okay, now why is this especially impressive? Well, because data keeps growing, right? There's always more and more pages every day. There's more stuff on the pages, so the index entries will get bigger. All those pages need to be ranked. There's more content, more objects Google has to look at, and more users spending more time on the internet, right, doing more searches. So all that, in the face of all this increasing traffic, right, and increasing computational costs, Google is still holding pretty well with that about a half second time. And of course, indexing is the key. So, right, Google matches these search terms to the web page content starting with text, right? So if we do an index like a very, very small scale, suppose we have the word syzygy, and that's stored in 4 pages, A, B, C, D. And if we have the word zygoma, that's stored in 4 other pages, B, E, F, G, right? So you can already see that's stored across both feet. And ziziva, another oddball word, stored in pages, right? Some pages there. So, when Google enters some search terms, it can very quickly grab the pages containing them. For example, if somebody does these 3 terms, Google can say, well, whatever you're looking for, it has to be on these pages because these are the only pages I have that match, right? Now, what might be the best matches is either these 2, because they're both on B, or these 2, because they're both on A or C, right? But I don't have any crosses with that. Also, these 2 are both on F. So I have some pages that contain 2, I don't have any that contain 3. So Google has to say, well, how do I prioritize? Well, chances are, if I enter in the words in this order, it's going to think the one that has the first 2 is probably the best match. Okay? Anyway, but that's part of the ranking algorithm. So when a Googlebot scans a page, how does it build this entry in the first place? Googlebot goes out, scans a page, delivers that page data to the indexing system, captures all the words from the page, and so if Googlebot goes to page D, and finds that it has the word syzygy, and D isn't already in the index, it'll add D to that index entry. Say, oh, here's one more page for that index entry. Okay, now why indexing is necessary? Well, the short version, a relatively small amount of overhead, right? Setting up the index saves a lot of actual real-time processing when people are sending Google to search queries. So, imagine this. Imagine you have a big stack of books, right? Some arbitrarily large stack of books, and you want to find out which of those books, if any, reference Charles Babbage. And let's also assume that, like a computer, you have no idea what the meaning of those two words is, right? No idea. You don't know that Charles Babbage is a human. You have no idea that he was a man or that, he's a 19th century guy. You don't know anything about that. You're just trying to decide, do the books contain stuff with those two words? So, very slow approach would be to read each book from front to back and see if there's any reference to Charles Babbage in there. Very fast approach, of course, check each book's index. Or better yet, build an index encompassing all of the books, right? That would be the best case. So you just have one document you have to read. All right. So the next thing, why distribute? Well, what is distributing? In this context, what we mean is this, like with our old friend, the MapReduce algorithm, right? Suppose we have a slug of text that is very, very long, okay? Very long slug of text, say 10 gigs, right? A humongous chunk of text. If we try to get one computer to process that whole thing, it's going to take a while, okay? For example, if we try to have one computer search this entire slug of text, it could take minutes, right? Depending on how good the search algorithm is. It could take a little while to get that done. Okay? On the other hand, if we take this slug of text and we cut it into slices, again, some arbitrarily, oh shit, that's what I should have done. That's what I'm going to do. All right. Something like that. Okay? If we take this entire slug of text and we chop it up into many, many pieces, okay, into 1,000 pieces, and send one piece to each computer, each of 1,000 machines, the search gets done in a fraction of a second. Okay? That's the basic principle here. If we have some giant slug of text, yeah, we could search through it all in one machine, but it's going to take a long time. It's going to take the time for one to do that. But if we have a system set up where, okay, this big slug of text comes in, and we automatically chop it up into slices and send it to 1,000 different machines, we're distributing the task over those 1,000 machines, it gets done a lot faster. The same workload is there, right? Because still, right, all these computers are still looking through that whole big slug of text, but you get the results 1,000 times faster. Okay? All right. So that's what distributing is. Anyway, so suppose the stack of books is very large, right? We have a library of books. Same example about looking for Charles Babbage. And suppose, like most humans, you only have one set of eyes. So you can only look, through, say, a book index every few seconds or so. Even an index search could be slow, right? If the pile of books is large enough and the humans aren't very fast, it's going to take a while. So what can you do? Well, get a bunch of your friends together, right? Gather N people, split the book into N substacks. Each person searches one substack, right? You get the job done a lot faster. Takes more people to do it, but you get the results faster. Okay. And this is basically the same thing as indexing in a distributed system. you have some very large index entry, right? We've seen these things for sports, for example, return literally, 20 billion pages. We don't want to have one machine searching through and evaluating those 20 billion pages against each other. We want to break up the task, okay? So again, each machine only does a small fraction of the total work. All right, build on that. So, suppose your search operation, word gets out that you're able to search through books very quickly. Word gets out and it gets popular. Suddenly you have millions of search requests every day. Sounds crazy, but here we are. Now a few of those searches are very common. Most of them much less so, right? So you have a lot of unusual searches, uncommon searches. But some, maybe like 30, 40% of your search traffic is from a fairly small number of searches, like 100 different searches. Okay? Well, on top of that, let's suppose one of your people is super fast. One of your people is like Olympic grade searching and can remember all those results from the last 100 searches. So has finite memory, but still can remember all the results. So anytime one of those really popular searches comes in, boom, give you the results back. So the first execution of a search happens normally. Even though that person is super fast, right, he still has to, even though he has perfect retrieval, he still has to go through all of the process to read the books and see what's in there. But once he's done it once, he can do it again basically instantly. Okay? So, what's the best way to use that talent? Well, essentially caching, right? You have this one person, he's super fast because he can remember all this stuff. Use that just like cached memory in a network system. Say, oh, here's a popular request. We'll store the results for that popular request in RAM so that anytime that comes through, boom, we can just instantly return those results. Searches that are less common, right, those get kicked back to the hard drives. Okay? Exactly the same thing, except with humans. Okay, so that's the idea with indexing, and those are basically the types of tools Google uses. Now, at a very basic level, right, pages can be indexed just by search terms. And this is great if the terms are very rare and they're on mostly text pages, then it's fine. But if they're for popular searches with a lot of synonyms on object-heavy pages, then it becomes kind of tricky, right? So Google's working semantically to match the user's intent. Google wants to figure out what you're looking for, how it might be described in different ways, and then return it to you afterward. So the indexing process, it can incorporate that kind of semantics, right? Basically, it creates entries for term groups or concepts, okay? So, for example, popular search to buy a car. Google might have, over the years, empirically observed that people who search for buying a car are more interested in car dealerships, right? They're interested in actually buying a car as opposed to how to buy a car or, various price comparisons. People who look for buy a car, they want to click on dealerships and do the comparison process themselves, okay? Now, that kind of feature could be integrated into normal search. Google could recognize, for this match, right, this subset of pages tends to rank higher. Or it can be contained separately in something called the knowledge graph. So the knowledge graph is basically how terms are interrelated as far as Google understands what things are. We'll talk more about that in a little bit. Okay, very soon actually. All right, so semantic units, right? Here's one way that this is the basis of the knowledge graph essentially. So search engines like Google, they want to consider how terms are used, how they occur. So example, as humans, we know that Charles Babbage or Babbage, Charles, we know that's somebody's name. We look at that and say, yeah, Charles is a name, Babbage, it's weird, but yeah, that's probably a name, that sounds plausible. Okay, now if you look in a book index, it's going to store Babbage, Charles, right? It's not going to have separate index entries for Charles and Babbage, right? Not gonna, right? Because Charles Babbage is a person, and people are listed a specific way in the index. And so as readers, right, we certainly see the difference between or Charles Babbage, where it's like or this person, and Charles or Babbage, in which case these are two different things, right? As humans, we intuitively get this. For machines, it's a lot harder to make them understand. So, what goes into a typical unit? Well, index entries are semantic units, which means one or more words with a specific meaning. And essentially, an index entry that has, multiple flavors of the name, for example, right, there's a pretty good chance, if I'm looking for Charles Babbage, index entry for Charles Babbage. Could be Charles Babbage. Could be Babbage Charles. Could be just Babbage. He's a sufficiently famous Babbage that I don't think there's any others worthy of mention. What else? If I knew his middle initial, it's probably an A. Let's go with that. Charles A. Babbage. Okay? All these are equivalent in Google's eyes. Okay? So the advantage, number one, find exact matches for multiple search phrasings. Okay? If you enter the terms in a different way, you're still going to get the same results, right? This is part of their things, not strings approach. So any pages that have some of these, the search for this is all going to be equivalent and return these same things. What's the other one? Saves a lot of space, right? You can imagine that there are many search entries for which, right? These are going to be, there are going to be many index entries that can be described in multiple ways. And instead of having a separate entry for every single one of those possibilities, which is going to exponentiate how much data they need to store, you just say, oh, these are all the same thing. We only need to store one copy of this whole long index entry instead of 4. Okay? And because a lot of space is saved, results can also be returned faster. Right? Less processing. Faster and cheaper, let's say. Less processing time, less processing equipment and electricity. Okay? So, doing this, right, it's nice for the humans because it returns the better results, but as far as Google's concerned, right, there are some internal advantages as well. Lets them do what they do cheaper and more efficiently. All right. So we can in fact look up this Charles Babbage fellow, because I just want to figure out what his middle initial is. Actually, I'm going to see if Babbage turns him up. It ought to. Yeah, he's a top guy. He looks like Charles Babbage. Actually, he looks a little bit like he belongs on a Game of Thrones set. Anyway, what's his... Damn it, he may not have a middle name, but he must. Born in 1791. Charles Babbage, no, I don't know. Perhaps he doesn't. That's just it. Huh. All right. Not everybody gets a middle name, I guess. Okay? Anyway, so what goes into a typical index entry? Well, again, index entries are semantic units, and determine the most likely grouping, right? The intended grouping, that's going to help Google deliver better search results, but also get some extra benefits there. Okay. Next thing, filtering common words. So, normal user, right? Most searches, most of the time, you're going to look at what's on the first page. You're probably most of the time not going to go on to the second page. Google's algorithm is good enough that way. Typically, most people only look at the top few. For example, right? What's a movie that's out these days? I don't know. Let's see. Is there anything I want to see? RottenTomatoes.com. What do we got? Sure, thanks, whatever. What's coming up? Shit, nothing. Well, we saw Toy Story 4, so fine. We took the kids out to see that last weekend. Toy Story 4. Now, if I'm searching Toy Story 4 at this point in time, what am I probably looking for? Yeah, showtimes, tickets, that sort of thing, right? Information to help me watch it. Yeah, that's probably, I'm not looking for the IMDb article, probably. I'm not looking for a list of actors. It's still in the theaters. I probably want to see it. And there we have it, right at the top, right? Boom, showtimes. Because Google knows, oh, this movie's still out. This is what people are looking for. If I scroll down a little bit, right, there's some clips, whatever. IMDb article is probably the second one. Yeah, some other stuff, Wikipedia article, Rotten Tomatoes, review articles. Okay, but most of the time, yeah, the top few results is going to have what people want. That's the dream for Google. That's what they want. Okay, so most of the time, right, search engine's only going to deliver a small portion of the matches. We talked about that. You get millions and millions. You only see the first 100, 200, 300. On top of that, very common words like the, appear on most pages and should be excluded, right? Because number one, they usually don't materially differentiate pages, okay? Results with or without them tend to be identical. Number two, Extra ranking effort, right? Since those common words appear on so many pages, basically you get one long index entry that's basically the entire English language internet. And on top of that, that index entry would be very, very large because, again, yeah, huge. So all that is just going to require more time and effort. Google's going to kind of tune that out. But I can show you something. Chicago Cubs gives you one set. Okay, and then I'll do it on the other machine. So if I look up Chicago Cubs right now, this is what I get, right? Their next game, what their ranking is, blah, 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 some upcoming games, some minor articles, whatever. Interesting thing, so I'm going to drop out of this and look at the this machine. And we can do the same thing on... Not even powered on? Forget it. I'll go back to my old one. All right. But if I do, I'll do it on a new tab at least. The Chicago Cubs. I still get this, but I get a little bit of different stuff too. Or at least I used to. No, maybe because I did it all in the same browser. Chicago Cubs on Google. Yeah, there's all the same. Website. Oh, that one, yeah, okay, good. Did I get the two panels with Twitter? Top stories. I did get a little different. Okay, so here, this part is the same, right? Chicago, what's that? Damn it. This whole lecturing thing is harder than it looks. Okay, so this is the page, just Chicago Cubs, right? And I get this panel showing the showtime. For the Chicago Cubs, I get the same panel and I get the baseball team article in the margin. I scroll down, I get top stories and Cubs on Twitter. Here, I scroll down, I get top stories, and I get official Chicago Cubs website. It's slightly different. This is one of the ones that, right, and there's the website below, and below that I might see Chicago Cubs baseball. Here's some videos, Cubs schedule. It's a little different, right? And here I get history of the Chicago Cubs, which I don't get on this one. And I think that's the real difference. So the interesting thing, a few years ago when I first started doing this and talking about how Google basically ignores the word the, and I said, oh, let's try the Chicago Cubs. And of course, you know, anything you try after saying something is always going to be, oh, look, and they are a little bit different. As far as I can tell, the likelihood of the Chicago Cubs being different, if you use that particular phrase, it gives a sense of there's some historical stuff here, right? Like I'm looking at, you know, the Chicago Cubs as far as, you know, a franchise going back 100-some years. Where if I'm just looking Chicago Cubs, then I may be some person who's just, you know, looking for different kinds of stuff, like current things. Maybe Chicago Cubs, I'm just looking for the next game, whereas the Chicago Cubs, you know, I'm an older person and I'm staying at home and I want to find out some stuff about the team. It seems to be something like that. Most of the time it doesn't really make a difference, but yeah, now and then it does. Okay. Anyway, a few things here. These are related, so you don't have to read these articles, but I'll give you the gist of what these things are. So number one, caffeine. Caffeine is a new indexing structure. And the short version of it, again, this is a little bit beyond the scope of what you need to know for the course, but I'll describe it anyway. Okay. Old system, spiders went out, grabbed pages, stored them in some big batch, and at the end of the day, the index entries were updated. Okay? That's the old system at Google from, I don't know, 10 years ago or so. This is the way it worked. There was a batch add of new pages at the end of the day. The new version with caffeine, newish version now, spiders go out and still grab pages, but those page updates are just about immediately entered in their index entries. Okay? Basically, it runs a lot faster. And what this is, essentially, This is, well, basically relaxing more acid properties of databases. Okay? If you want to make sure that at the end of the day that everything is perfectly matched and any search that comes in at the same time is going to retrieve exactly the same results, right? If you're holding to acid properties, you basically have to do something like that because you can't, update one copy and be worried about the other ones being available, things like that. Okay? But with caffeine, what happens? Number one, portions of the whole index are essentially isolated from each other so that small changes can be made without locking up the big system. Okay? It's basically designed from the scratch, right? If you're insisting on acid properties, that's one of the things we talked about is anytime you want to make a change to it, you have to lock that part of the database so that nobody else can access it so you don't get some kind of dirty read. But with caffeine, they've restructured how it's stored, how all this data is stored, so that they can make small changes and they only affect, the local spot where there is. And Google on top of that, the whole system is more tolerant. If you get slightly different search results, Google says, yeah, you know what? Yeah, you get search results that are a second out of date. But that is a lot better than having to wait till the end of the day to update pages anyway. Okay, so again, all I'm going to ask you about as far as caffeine ever would just be that it is a new indexing architecture, right? So pages come in and they're processed and the index is updated faster. That's the thing about caffeine. But this is essentially the logic behind it. Okay. The other thing, Hummingbird and semantic search are closely related. So semantic search has been around for a little while at Google, but it was only in the last several years that they applied semantic search to the entire Google process. It used to be, for a few specific things they applied it, but Hummingbird is part of the engine, basically, that processes semantic search for all search queries. So that's what Hummingbird is. We know what semantic search is, trying to match the user's intent, not the exact text. Hummingbird is the technology that enables that to happen at Google. Okay. Last thing, knowledge graph. Okay, so I'll talk about the knowledge graph for a minute. Who is a famous scientist? Give me the name of a famous scientist, but not so famous as like Einstein or something. A famous scientist. Who's a famous astronomer? How about that? There's one people always get. Oh, all right. I was expecting Hawking, but yeah, Galileo, that's a good one too. All right. Okay. This over here, this is what's called a knowledge card, and it's basically like a short Wikipedia article. Now you see down here, right, some of these other names may be known to you, right? In case anybody doesn't know, right? He lived around 1600 in Italy, and he got into some trouble with the church for basically saying things like the planets revolved around the sun, not that the earth was the center of the universe. Anyway, so other people that get searched for, right? Copernicus, who came before him, Newton, who came after, Kepler, who came before him, I believe, it looks like 15th century, and Aristotle, who came way before all of them. They're all related, okay? And if we want, we could view some more. Let's see some more. This is the knowledge graph up here. These people are all related in some sense. Now, how they're all related is they're all scientists from, John Locke, I don't believe, was a scientist, social scientist. But, okay, and Edison, well, I don't know, he's more of an engineer than a scientist. Martin Luther wasn't. Machiavelli, interesting. I guess some of these, it just drifts off from science people into, pre-industrial notables. Anyway, the way the knowledge graph works is this, like this. So let's take a fellow like Galileo. What do we know about Galileo? Right? Astronomer, experimental physicist, if I'm correct, and my memory's a little fuzzy, he may have been the first guy to show that things accelerate, right, as opposed to, yeah. All right. Excuse me. So that was his thing. And also, right, we again know he's 1600, let's say circa 1600, notable. And the knowledge graph basically links up those things into categories, right? So Galileo, as an astronomer, you know, he belongs to this list of astronomers with people like, you know, Hawking and, I don't know, I'm not really, Copernicus, sure, Kepler, Brahe. Anybody heard of Tycho Brahe? No? It's a very interesting story. More interesting than this lecture, I suppose. I'll digress for a second. Okay? Tycho Brahe, very interesting guy. He died in a strangely horrible way. So, he was at a party, right? So back in the day, if you were a science guy, you didn't just have money to do science, right? You had to get research grants, just like they do today. But the way you got research grants in those days, you found some king or some rich guy who'd put you up at his house for a while, and pay for you to do research. That was the way of the world then. So anyway, he's living with some rich guy. I forget if he's a king or a baron or something. Living with some rich guy who's funding his research. And the rich guy has a big party, right? A banquet, has a big party. And of course, it's like 1600, so everybody's drinking a lot. Well, he's had a lot to drink, and he really has to pee. Well, the guy who's giving the party is actually at the moment having a very, very, very long toast, because in the pre-industrial days, nobody had shit else to do, so everybody was very long-winded. So the guy's giving this very long toast. He goes on like a half hour, maybe an hour, whatever. And all the time, he's sitting there saying, oh man, I really have to pee. I'm gonna fucking die if I don't. Well, sure enough, his guts inside ruptured, and he did die from not peeing. Science fact. All right, you can look it up anyway. But he was a famous astronomer, and that's how he went. Because he, you know, it was considered very rude to get up and pee while somebody was giving a toast, especially basically if that was, you know, like the CEO of your science operation. So yeah. Anyway, but back to this. I bet you guys didn't think you'd learn about the dangers of not peeing today. Okay, so Google groups all these into astronomers, okay? But astronomers can likewise be grouped into scientists, right, of various kinds. And all those are part of their group. And there are different boxes in here, right? There could be chemists, biologists, physicists, whatever. Biologist, damn it, right, whatever else, I don't know. And there can be linkages across those. And this is the kind of mapping that Google does, so it can kind of understand semantically what people are talking about. If you're looking for Galileo, most people are looking for information about him as an astronomer. But they might be looking at some physicist stuff, or they might be doing, you know, some general stuff about people who were, you know, from the 1500s, 1600s, whatever. And there's different boxes for those, right? And he could appear in both of those since he lived in both centuries. Okay, and that's where some of these other people come in, like, you know, 1500s, you have guys like Machiavelli. He shows up there as well, and Galileo, let's say. Okay, so that's how basically Google comes up with these linkages. This is the knowledge graph. It says, this person can belong to this group. He could belong here. He could belong here, right? Okay. That's the knowledge graph. And that's the basis of how Google says this thing is like this other thing. It says basically Galileo is a lot like these guys and not very much like these guys. Okay? You can look at like cross-membership groups, things like that. And the cross-membership groups are sufficiently strong, then it'll say, you know what, these two things are basically the same thing. All right. Okay, but again, all that stuff, not going to be detailed questions about that. Just know what these things are. Okay. So, how does the indexing system work? Well, let's consider it, to start with, Every request, right? Every request goes to a cloud system. Google has some cloud. How does that work? Well, we know the tasks, we know what happens in principle, but we don't know all the details about how the system is put together. And that's actually wonderful because it's really, really complicated even for terribly smart people. This is not something you want to have to keep up in your head, right? All these large-scale systems these days, they're designed in a modular way. They're designed as loosely coupled systems so that basically when you send a query to Google, so if I send in some search terms like Galileo, and I send that to Google, I don't really need to know what goes on in there, right? Google needs to know, sure. All right, so what happens in there? Here's Google. But the point is this, Google can design a system that's going to accept any kind of, anything you can enter in a search text box, it's going to be able to process somehow. Okay, so this is all broken up into different parts. So what we can ask, what tasks are required to handle the queries, what's the sequence of the retrieval process, and what are the interfaces that happen in between? All right, well, the first thing, just like Facebook, right, and all these other big operations, Google doesn't serve everybody from one location. Reasons why, number one, if you have all your eggs in one basket, it's a more fragile system. Number two, you want to keep locally relevant data closer to the users, right, because that makes it easier to deliver the content they actually want. And of course, energy costs. So the cost, if you have to always send information from halfway around the world for many, many queries over and over, that's going to add up. So Google wants to keep the local stuff local, both for performance reasons and for cost reasons. Still, Google could do that, right? One of its data centers could probably handle its whole worldwide search from about 10 years ago. They're sufficiently big, because Google only has like 15, and you can look at the math and say, yeah, they're doing 15 times more search now, so one of them now could have handled the old search. They could probably build one big enough to do it. They just don't want to for these reasons. All right. Now, you may have heard of Google's data centers. If you haven't, you have now. What they are is basically giant server clusters, right? So big warehouse-sized buildings with tens of thousands of servers. The details, Google doesn't talk about them a lot. There's a lot of secrecy involved. But, get this, some older articles. This is from 2017. So we got here. So you can get, I believe this one has a little picture. Sure, let's continue to the site, yeah. Okay, find cookies, wonderful. Okay, so if you look closely here, if I can actually get it to scroll successfully, I gotta zoom. There we go. That's weird. All right, I gotta drop out of my presentation. There we go. Those things there, right, it's hard to see what they are, but those are just giant columns of servers. So they go on for a long way, and they go on for a long way that way, and each one of these is a stack of a whole bunch of servers. That's what they do. That's what's in a data center. Okay. So, each server cluster, right, what does it do? Well, every task that comes in gets split into sections and distributed over that set of servers. So, a task comes in, like there. First question, we're going to say, check for local storage, right? If Google has the pages to match this search request locally, then it handles it. Let's assume that they do. Assume for now they do. Okay? So what happened? First, parse the search query. Look at all the terms in it, figure out what they are, extract any semantic units. Second, find which servers will have the matching pages. Okay? That's an important thing. Remember, Google has tens of thousands of servers in here. It doesn't want every query to get run through every server. Ideally, right? Ideally what will happen A search can be handled by a small fraction of all the servers, allowing parallel operation. Which just means Google has 10,000 servers. Hopefully a query comes in and all the pages corresponding to that can be stored on 1 or 5 or maybe 10 servers, leaving the 9,000 and change other ones able to do other stuff at the same time. Okay? That's the kind of parallel operation we want, or Google wants. I'm not getting paid by them. Okay. Third, pulls the index entry, compares the pages, okay, and returns the short list of best matches. All right, so we understand what's going on here. This is the basic process. We'll talk about how the servers are arranged in just a minute. Okay. But I will mention, functionally, it's very similar to a RAID device. Remember RAID, redundant arrays of inexpensive or inexpensive is the correct one, or now I forget what the current usage of the I. Redundant, independent disks, but originally it was inexpensive. So it's a lot like that, right? Basically, Google's whole data center operates like a gigantic RAID device. So the traffic gets handled through a common interface, right? Everybody comes in through that google.com site. The query gets directed to particular machines, right? Just like in a RAID device, you're storing a file and you're not mirroring or striping. It gets stored to one volume of the drive. Same thing here. The query comes in, it gets processed by some small subset of servers, not the whole stretch of them. And it can include some kind of parallel processing. Just like RAID devices can do striping to do anything faster, Google, same thing, right? If it has 10,000 servers, maybe it slices up the task and divides it over a few hundred servers in order to return the results faster, just like striping in a RAID device. So, if you understand RAID devices, you remember that from our first section on Facebook, you already know like about 2/3 or so of how Google's going to do their system. Okay. Now, for a moment, let's assume Google keeps a master copy of all data. For any particular copy of a page it keeps, it says this is the authentic real copy. Now, it's not clear if one data center does that. If they're saying like one of their Silicon Valley ones, that's the data center that keeps it, it's not clear that that happens. It's also not clear if Google ever maintains master copies as such, right? Basically, any page is going to keep at least 3 copies of it, but they could all be considered equivalent to each other, right? And just if one of them, something goes wrong with one of them, Google looks at the other 2 pages or actually goes and consults the website itself to try to figure out what went wrong. Anyway, though, 3 copies are enough for parity checks like we talked about. We can recognize when an error occurs and we can pretty certainly recognize what the error is. But those copies could be stored in separate data centers, right? There's no absolute certainty that even though Google has triple copies of things, that they're going to be stored in the same data center. And this applies not only to web pages, but like to anything else you store on Google too, like your files in Google Drive, for example. Anyway, what is known, data centers do have different capacities, different content. Some data centers will have things that other data centers do not. So we know there can't just be one data center that has the master copy of everything, because it's not going to have everything, because it wouldn't make sense to keep all that in one place. Anyway, the way Google works as far as finding stuff, so if a page isn't stored in the local data center, it has to be retrieved from somewhere else. I'll draw a little map here, down here in the corner, and then we'll throw it away in a second. So suppose, what do we have here? Japan, Australia, West Coast, I don't know, Seattle, UK, New York, sure, and Florida, I guess. Okay? We'll put in the text. Japan, Australia. We'll make it Canada. That can be Vancouver. This can be Silicon Valley. This can be New York. This can be Disney World. Okay, whatever. Anyway, so Japan is a good one for this because you know they're going to have a lot of Japanese language stuff. These other data centers, not so much, right? Not saying they might not have anything, but chances are not much. So, suppose, for example, a request comes in for some local New York news, right? And it comes in from some American person who happens to be in Japan. So, U.S. expat sends query to Google.Japan, right, for latest New York news, right? Good chance that's not going to be stored locally in Japan servers, whatever detailed stuff he's looking for. So, what happens? Google Japan doesn't hold those index entries, but there is basically a digital arrow pointing to the New York data center that basically says, I don't have it, but if you want to find it, this is where to go. So it kicks the request upstream to the Silicon Valley one that's at the top of the hierarchy, and that one passes the result, passes the query on to New York. New York passes the request, passes the results back. Silicon Valley passes them back. And as long as that's a pretty unusual request, it's okay for it to happen that way because it just doesn't happen that often, right? But if there start being a lot of requests for that sort of stuff, eventually those pages, even though they're not in Japanese, they will start getting cached locally at Japan's data center, so they don't always have to make that, trip back and forth. Okay? That's the basic structure of how all these different data centers interact.